Welcome to 16th lecture on structural stability. So, let us briefly recall what we have covered in the previous class. We are discussing about post-critical analysis of plate. So, post-critical analysis meaning that it means that we are studying the behavior of the load carrying behavior of plate beyond buckling, and then we have seen in order to do that we have to consider the in-plane distribution of forces. So, in-plane forces are no more treated as constant, but we allowed them to vary, thereby we are allowing them to redistribute, and then we have solved it, and the solution was a little ad hoc, but it was given, it is a very simple solution, a little ad hoc, but it was given by Volmir, and it essentially captured the physics. So, we have successfully demonstrated the redistribution of stresses. So, we have seen that just on the verge of buckling, it is subjected to uniform compression, right? And in the pre-buckling regime also it is uniform compression, but then as soon as it buckle and then we go increasingly, compress it beyond critical load. So, here Nx we are going beyond critical, okay. So, then what happened? This force, start redistributing, right? So, end portion start carrying more load, and whereas the middle portion load is basically load carrying load basically reduces, right. So, this kind of redistribution occurs, and as you go more and more, this will carry more load and this will go less load or something like that, okay. So, at the end we may assume that the essentially load are carrying by the two end strip, right, and from there we have told that there is some concept like equivalent weight concept for this, and that has been adopted in American and Canadian code, okay. Equivalent weight BE, okay. And then what happened, along the transverse direction there is also redistribution occurs, and there what happened, that end strip earlier in the pre-buckling regime or even on the verge of buckling there was no compression, no forces in the other direction, but when in the pre-buckling regime the other direction also forces develop. Of course, for redistribution to occur, these plates at the end, the other direction, the end, the edges on the other direction, y direction must be adequately held in the in-plane direction, okay. You have to, okay, that is what, otherwise if it is not restrained adequately, it will not develop the it will not allow to redistribution to occur, right. So, that is very important. So, redistribution of in-plane forces largely depend on what is the edge conditions at the upper end, and then the end strips are still carrying a compression load, but in between they carry the tensile forces, okay. So, that is what basically happens, and then these tensile forces allows the stiffening of the plate. You see that we have all noticed the erosion in stiffness out of due to in-plane forces, right. When it is under compression, then we have seen that how it erodes the out of plane stiffness, right. So, but tensile force also lead to tensile stiffening. So, that is what essentially happens, right. So, that we have discussed, and this solution we have followed was given by Volmir around 1960s, right. So, a little simple solution, but more rigorous solution can also be obtained, because that equation, if you can recall, the equation for plate buckling was numla square d wxy is equal to nx d2w dx2, right, and nx we took as we express in terms of stress function d2 phi del y2, and that is multiplied by thickness h, right. And then the compatible equation we have obtained in terms of w and x, okay, in terms. So, there are two equations and two unknowns w and phi, right. So, here we will see that this equation is of course non-linear, right. So, nonlinear differential equations or nonlinear equations, differential equation can be solved using perturbation technique, okay. Perturbation technique, okay. So, perturbation technique is a method for solving the nonlinear equation. What we do, in the non, we assume whatever is the field variable, for example W, for example phi, we assume this to occur in the asymptotic series. Okay, so what we assume W to express in using an asymptotic series, W into epsilon W1 plus epsilon square W2 and something like that. Okay, so epsilon is a small parameter that controls the non-linear eventually. Okay, epsilon you may explicitly derive from the equation or you may not. And this asymptotic expansion is valid when epsilon is small. Epsilon is a very small quantity, very less than 0. In case any equations you and there are several variant of perturbation technique, that's not a problem. In nonlinear dynamics, okay, you consider Duffing oscillator. So there you will see that here Poincare Lindstedt state perturbation, because there not only the field variable but also the the frequency need, nonlinear frequency need to perturb as well. Okay, so this is similar to that. So if you people have little idea about that, then it will be easier to understand. So epsilon is very small parameter, yet it is basically control the degree of nonlinearity. It can be directly related to degree of a nonlinearity in the system, non-linearity. I am not going into details, but to give you a little idea. Similarly, the other field variable can also be expressed as epsilon phi1 plus epsilon square phi2. Please note that you may wonder that whether the series is convergent or divergent. Do not worry about convergence and divergence. These are asymptotic theory. We don't care about the but yes, being epsilon small, higher terms will increasingly contribute less and less. So it's that way it is basically convergent effectively, right? So then we substitute the differential equation, and then what happened? We equate the term associated. So when you take this kind of field variable and you substitute in the governing equation, nonlinear equation, what you will see? Then you basically equate the, so then you rewrite the equations in terms of something to the power 0, one equation plus epsilon to the power 1 equation plus epsilon to the power this equation is equal to something, right? Right hand side also similar equation. So then equate the coefficients associated with this varying power of epsilon. You understand? Thereby you will see a nonlinear equation can be approximated as a series of linearized equation. And then at the end, once you find out W0, W1, W2, you sum them up and then you will get the solution. Understand that? Now, a priori, if you don't know what is epsilon, later you can use the other conditions in boundary condition and other to find out what is epsilon is. But in many instances, epsilon you can explicitly determine through scaling of the equation this and that. Okay. Now, because we have already expressed the in-plane forces in terms of a stress function, that's why we treat epsilon sigma, the stress function as also field variable. But please note that there are perturbation technique in which we don't require to express nx in terms of a stress function. Rather, we can directly perturb nx. So you will see that nx can also be expressed as nx0 plus epsilon 1 in x1 plus epsilon 2 epsilon square nx2. So this kind of perturbation is also, and you do not require to take many terms. This is the first order equation, this will give second order equation. First, this is 0th order equation, this is first order, this is second order. Okay, that way you can also do. But here I will just show it once. Quickly we will go through. This is a little, it involves lots of algebra, that's what I don't do that, but I will just show you so that you have a little idea about that. So please look at this screen like when. So well, I will not go. So here I am referring to state perturbation because this is a specialized technique, but essentially will give you the feel. So I have used it. So one of my previous PhD student who worked in this, so he derived all this. Now all these equations you already know, right? Because this we have derived, right? So ultimately we arrived at these are the governing equation, right? This is the governing equation, right? Along with that we get the boundary conditions. So at this age, WW, the simply supported boundary conditions, right? And then this equation is coming P, if P is the axial force being applied, right? Then you can integrate over the in plane forces over the edge, then you will get the equilibrium equation, right? And then you can for edge y0, you can also write this equilibrium boundary condition, right? Simply support it. Similarly, there is no in-plane forces on y direction, so integrate and make it 0, but in the other direction there will be in-plane shear, right, because of the restraint. Now, you can also express the unit shortening. You integrate the strain over the length and then you divide it, or divide over the edge length for getting the unit shortening per unit width for both the x and y direction, right? Then we assume the solution W and phi. There are two field variable W and phi, right? We assume epsilon is a small parameter controlling the non-linearity in the system. So, epsilon to the power n W. Please note that epsilon to the power n, 0th power means anything to the power 0, 1, right? Epsilon 1, W1 plus epsilon. You do not require to have a two-term approximation is good enough for this, okay? Sometimes you take three-term approximation, two-term approximation, 0th order, first order and second order is good enough. Then you substitute and then you get the linearized equation. So, you say these are the linearized equation in terms of phi 0 and phi 1. Then these are the linearized equation of phi 2 and this is in terms of phi 3. Of course, here it is homogeneous equation, but then phi 2 and phi 3 in terms of W1 and W1, W2. So, you see that somehow if you decide phi 0, then you can get the phi 2 and then you have to assume some W1, then you just substitute that, you will get phi 2 and with assume W1 and phi 2 and assuming something W2, then you will get. So, all this linearized equation, and you can, it is easy to solve linearized equation because we know that how to solve linearized equation. In fact, nowadays with the advent of this, the symbolic computation in Maple and Mathematica, you can do these things very effectively, okay. That is what we did, because then otherwise the equation become very complicated. I have seen the equations, for using perturbation, then it takes, an hour, several hours to do these things, okay, but it's very, beautiful actually, yeah. So, then you see linearized equation, I am writing all these things, all equations, okay, in terms of W1, W2, W0, W1, W2. So, I will just see that. So, what will, this is order of 0th order equation. This capital O refer to order, okay, order 0th order equation. Nambla square, P0, 0. Nambla 4 is not the correct thing to write, but people write it. It is Nambla square rather, okay, to Laplacian. So, then for the solution for the 0th order, this can be expressed as phi 0 is something like this, okay. Then phi 1 and then W1 in the first order equation in terms of phi 1 and W1, okay. Then you will see these equations, the solution will be phi 0 is there. So, if you take phi 0 and substitute, you will see that phi 1 will be for these equations, it can be taken as it will be identically 0. You do not require to have phi 1, okay, that will satisfy this, because this becomes identically 0. And then W1 we can assume some kind of, because it is linearized equation, sin. So, by satisfying the boundary conditions, assume the sinusoidal, right, as you double Fourier series, right, and then you substitute this equation and this equation and phi 0 in 16b, then you will get the unknown coefficients, right. Similarly, second order equation, now you will get the equation for phi 2 stress function, second order approximation for the stress function, right, and second order approximation for the W2, right. You see another two equation in terms of Laplacian. Right hand side, whatever you have obtained, whatever in W2 or whatever term you have obtained from the previous equations. Here once again for 18, you see one of the equation phi 2, that if you solve this equation, because this is a linear equation, so it can be expressed in terms of this. But once again, it is found out that W2 can be identically satisfied with this kind of approximation. So, W2 is 0. Then you substitute this expression in this equation 18b, and then you these equations, and then from there you will get the unknown coefficients, okay. Now, you take third order equation, third order similarly phi 3 and then W3, okay. Once again you see that, so it is changing in one approximation, phi 1 is being 0 and W2 is some expression. Another one, next order approximation, W is being non-zero, but phi 3 being 0. Why this thing happens? I can tell you some analogy, because this is happening because of the symmetry and anti-symmetry of the mode shape. Okay, This can be, I mean, I am not going into details, but I can recall when we were doing these things, this can be beautiful, there is a very beautiful, physics behind this, okay. Because some displacement field or some, field variable being symmetry. So, all the center symmetric terms will be 0 over there, you understand. So, that is the reason. Anyway, so then with this kind of progression we can get all these things, and then finally we will get the asymptotic solution. Why asymptotic? Because it is associated with epsilon 0, epsilon square and things. You please see that in phi, you see that phi is what? Even. Phi is a even function. Phi is a even function. Why phi is even function? Because it is appearing xi square. It is even in terms of xi. You see xi 0 and xi square. Whether W contains term xi, epsilon and epsilon cube. So, 1 basically contains odd term of epsilon, the stress function, the even term of stress function, whether the other contains the odd term of in terms of epsilon. So, that is the difference between phi and W. So, the approximation, that some approximation, epsilon, whatever is associated with epsilon in terms of, the same term in phi is equal to 0. So, then this why we call this asymptotic solution? Because it is coming from asymptotic series, right. And then whatever unknown coefficients, then you can enforce the boundary condition. So, then equilibrium condition, you see that from here to you will get the equation, then another equilibrium, you enforce this boundary condition, you will get P, okay. End shortening you can also find it out. Now, from here what is epsilon, that we do not know. Epsilon can be related with deflection, you see that maximum deflection is given by this. If you substitute in this equation, W max will be epsilon. Why W max? Because when you find out of plane deflection, you put x is equal to a by 2, y is equal to b by 2, W max is equal to epsilon a11 plus epsilon k a13 a31, and if you invert this relationship, you can find out epsilon a1 is equal to this. Now, you see what is epsilon now? Epsilon is nothing but W max plus something into W max cube now. So, do you understand from that how epsilon controlled the nonlinearity? See, epsilon is directly related to out of plane deflection. More out of plane deflection will mobilize, is causing more nonlinearity, because it is pushing it is mobilizing more post-critical redistribution, and that is you can clearly see from here, because epsilon is W max plus something into W max cube. Now, W max is a small quantity, if you right, it is a small, deflection will be much smaller comparing the in-plane forces. So, the smallness of epsilon can also be justified from these things, from expression 29b, right? Clear? So, epsilon is basically a variable which control the nonlinearity, which control the, in this case, which control the degree of post-criticality, if you think so. It can be a I do not know whether it can be considered to be a kind of order parameter. Order parameter, this concept is used in physics, it's a generalized term, okay, for a system behavior, how it changes, okay. It can become, so it's a term which control nonlinearity. And another thing is that it is smallness can also be justified in many instances. So, that is the way. I will send this to you, you can go through that, you do not essentially work it out, but have with you the concept that how these equations are solved, rigorous solution, because whatever we have done using Bolmer solution was a little simplified and ad hoc. And if you want to do research using Bolmer solution, you will never be able to do anything. You have to have a very, because science and work in this area has progressed long. So, if you want to contribute anything new solution, then you have to learn perturbation and asymptotic explanation things. Mechanical engineering people are very conversant with that, they do that. And in civil engineering we are little a little behind, okay. And this concept is not only applicable here, but please note that this is also equally applicable in nonlinear dynamics, okay. So, in case of a Duffing oscillator, when you try to find out a closed form solution, you will see that we use these approximations, okay. I will say what we do basically, okay, fine. So, what you do, let me tell you. You see, so here the field variables are W and phi. That's what we perturb it like this. But if we don't use this, if we do not use this, phi, we don't want to express it in terms of stress function, then we can directly solve the equation in terms of Nx. And please note that we can have a asymptotic expansion. There are literature in which this kind of expansions has been substituted. Okay, and there also you can solve it. So you see that. So zeroth order equation Nx0 is essentially, you will see that will give you the pre-critical whatever is happened, pre-buckling scenario. Then Nx1, Nx2 is the term which are basically contributing in describing whatever redistribution is occurring, and there is this influence change is occurring in the influence forces. Okay, so that is it. So in dynamics also similar analogy is something like U double dot plus omega square U right, plus say some parameter maybe epsilon U Q is equal to Ft. So we have learned about these two terms in our dynamics, right? Mu double dot plus K is equal to 0. So omega. But as soon as there is some nonlinear term that becomes, so this is called, so what kind of cubic nonlinearity? This is cubic nonlinearity, and there is a small term epsilon. So that controls the nonlinearity. You see similarity between these two. There you see that so EU, when you want to solve this equation is called Duffing oscillator. This describes the equation of a Duffing oscillator. Many problems, including the one geometric nonlinear problem, can be reduced to a Duffing oscillator problem. The vibration of nonlinear in presence of geometric nonlinearity. Okay, so U can be expressed as U0 plus epsilon U1 plus epsilon square U2, something like this. Okay, and you see, if you do and substitute, you will see that you will not get the correct solution. Okay, you will have a solution which you will not able to capture. At the same time, you have to perturb omega also. Omega will be omega 0 plus epsilon omega 1 plus epsilon square omega 2 and things like that. And this is called Poincaré Lind state technique. You have to perturb the equation, because it's in natural frequency will no more be constant. It will also vary. It's a nonlinear frequency. With response frequency will vary, it will change. So that change you have to capture. So this is called Poincaré Lind state perturbation. And you can similarly, there will be a linearized equations. Okay, first zeroth order equation, first order equation, second order equation, and all are linear. So you can solve one after another, and you can sum them up to have a asymptotic expansion for EU and also asymptotic expansion for omega. Okay, thereby you can clearly see that this is a epsilon will be a very small quantity, because that control the degree of cubic nonlinearity. First order, say third order term. Could you please tell me why cannot be second order term U square? F is equal to KU, right? So sign needs to maintain. If you use square term, that means if you are applying positive force, negative displacement is occurring. Negative stiffness cannot occur. There are devices that exist in control, structural vibration control or passive control, where you can have a negative stiffness device, that you can design, but not physical. In physical term, you cannot have a negative stiffness, right? You can pull a spring. There will be for positive displacement, there will be positive restoring forces, right? Anyway, good. So with this, I stop the discussion here on the plate, buckling and post buckling behavior. Okay, I will from here logically we should go to theory of cell buckling, but then I will not jump to the theory of cell buckling because we will cover the later. Right now we are going to concentrate on dynamic stability, how dynamics is important and why dynamic stability is important. Not only that there are various forms of dynamic stability comes into real scenario, but also the treatment itself will come there later. But before that, there is a small thing what I would like to demonstrate. All of you are aware about the Eigen buckling analysis for the frame. I will just demonstrate to you a computer program that I have written and I have shared it with you. So how that program is written? Quickly I will go through and I will send you by mail. Okay, I will show you the structures. Those of you who are conversant with the finite element coding, this is very simple, but I will emphasize two important steps here while coding. Okay, and that's true. This will be in parity with whatever you do when you do Eigen backlink analysis using commercial software, which are little advanced, not like STAD. Okay, using Abacus or ANSYS or things like that, which are little advanced software, which is added with advanced feature. Okay, not like STAD. So this thing was missing. So okay, so let me show it to you. Okay, yes. So please note here. So this program is very simple. It is having one main routine and then several functions. So of course you know the command. All of you are conversant with MATLAB programming, right? Clear all, because all variables are cleared, and then close all, and then CLC. Okay. Yeah. Now see, I am not very efficient coder. I mean, I cannot do a very efficient coding, but I will essentially give you the steps. So I am deriving. I am giving the input. So number of element, how many elements are there? Okay. So here, for example, we have taken a very simple frame, that is Gable frame, for demonstration, but you can use it for others. So here I have taken a Gable kind of frame. Okay, and this is used in industrial shed, right? Gable frame, right? This, and then I am considering this as a subjected to P. I want to find out theoretical value of P, right? So of course this is symmetric. So how many? So I am made discretization. These are all node. These are all node and these are all elements. So element is 1, 2, 3, 4. These are all element. Number of element 4, and number of structure. How many nodes are there? 1, 2, 3, 4, 5. So number of element is 4, right? And number of NS node. NS node means number of node in the structure, number of structural node. How many? 1, 2, 3, 4, 5. Number of structural node is 5. Number of structural degree of freedom. If the number of structural node is 5, each node has what? This is 2D frame, 3 degrees of freedom, U, V and W, right? So each node has U, V and W, theta, U, V and theta, right? So how many? 5, 15, right? 15. Number of element node. Each node has 2. These are all 2 noded beam column elements. So 2 node, number of node in each element 2. Number of degree of freedom in each node is 3. So this can be changed for anything. So I will demonstrate with respect to that frame. Now you see that load coordinate dot text means you first load a file which contains the coordinate. What are the coordinate? So so you see, when I am so can I open from here this one? This is PPT file though. You see, this is the way it is. You see, this is 0, 0. I am taking -3, 0. This is nodal coordinate. Okay. This is basically 3 meter. This is 5 meter. This is okay. Gable frame. I am closing it. So all this nodal coordinate I am giving as input, right? So you see that coordinate dot text. Coordinate dot text. You please see that node 1 -3, 0. Node 2 -3, 5. Node 3 0, 5, 3. Clear? Coordinate. Nodal coordinate. Then here what I am writing, basically I am just coordinate dot text, that I am transferring with a another array, coordinate array. So coordinate zeros, I am defining its size of the array, and then I am running a number of structural node or number of element node. Number of for all structural element nodes. So each node has coordinate, right? I, j, essentially transferring to another. Then I am loading the connectivity. How I can load connectivity? Means nodal connectivity. Each element is connected with 2 nodes, right? Number element 1 between 1 and 2, element 2, 2, 3, element 3, 3, 4, element 4, 4 and 5, right? So this is connectivity. Then I am basically transferring this connectivity to another variable LP node. LP node is the nodal connectivity area, which is of dimension n element any node. Now, I am also loading the loading and boundary condition. Loading dot text. Loading means I have a loading on the top at P. So, what I have to give? I am, you see that what I am in the loading, what I am giving? I am defining the node on which the loading is applied, node 3, okay, and there are 3 degrees of freedom. So, in each degree of freedom there can be loading. So, I have a only vertical loading. So, that is what I am giving, right. I do not care about the, I am just assigning a value of 1, because from the eigenvalue analysis I will get the value. So, here I am putting only 1 unity, okay, it does not really matter, okay, clear. Now, then I am putting the fixed boundary condition. So, node 1 and node 5 are basically fixed, and what are the degree of freedom fixed? U and V are fixed. So, these are all hinged. If you want to make it fixed at the hinge also, then these zeros should be replaced by 1 and 1. I am using a binary variable. If it is 0, then that degrees of freedom is not restrained. If it is 1, then that respective degrees of freedom is restrained. So, it is a binary variable, okay, clear, fine. So, then I am assuming all the area of the element are same. I is equal to second moment of area and modulus of elasticity, in the all are SI unit, Newton per meter square, right. E. So, then I am initializing the structural stiffness matrix, AST. Of course, you see its dimension will be number of structural degree of number of, I am initializing geometric stiffness matrix, right. Now, what I will do, I will find out the, first I have to do a static analysis. Why? Because I need to know, in order to form the geometric stiffness matrix, I have to find out the axial forces in all the members. So, if there is a vertically downward force at P, at top node, right, then I have to do a static analysis. That is what essentially you will see. All the software, when you do the Eigen buckling analysis, that must be preceded by the static analysis, right, because axial force, relative distribution of the axial force you should know, right. So, you see that, then when I am doing global assembly, this looping you must understand, because this is extremely important in all your finite, this is uniform to all finite element coding. I have to run total 5 loop for the assembly. I have to run a 1 loop over element, one I element to 1 to number of element. I am finding out that this element is connected with x1, y1, x2, y2, 2 node, this coordinate, and then I am finding the length is root x2 minus x1 square plus y2, right. Then I am cutting cos theta sin theta, that is the inclination angle of them, right. Then I am calling the stiffness matrix, material stiffness matrix, EST, this subroutine. So, material stiffness matrix, here you see that stiffness matrix, you see that these are the 6 by 6 stiffness matrix I have written. First I am populating the upper triangular matrix, and then for symmetry I am doing it, right. You see that this is the 6 by 6 matrix, and how it does look like. You see that this I have derived 6 by 6 matrix for this in using global coordinates. So, that is why it is a function of cos theta and cosine and sin theta. This is element stiffness matrix, and this is the geometric stiffness matrix, fine. So, then what we have to do, then after element we have to run a node over the node. So, for I node is equal to 1 to number of node, and LP node I means first node over which it is connected is LP node. Now, you have to recall the nodal connectivity, I element comma I node, right. So, first looping is over element, then looping over node, then there will be looping over degree of freedom, right. But please note that, because we have 2 degrees of there will be 2 indices I comma j, right, because stiffness matrix is a matrix, right, stiffness matrix has 2 indices. So, the nodal and degree of freedom, this looping should appear in twice, you see that. So, you see the first I will identify the indices which is fixing the row, and then I will have another index that will fix the column. So, that is why you see this LP node I is equal to, this is on node which it is connected, then there is a degree of freedom, no 1 to now. So, when I am going to each node, after that on each node there will be a loop over the degrees of freedom, right. So, I node 1 to number of degree of freedom, then I am finding out what is structural degree of freedom, and then what is element degree of freedom. IS degree of freedom and IL. So IS degree of freedom will be what? The global node with which it is connected to. So LP node I minus 1 into n degree of freedom plus I degree of freedom, and the element will be I node, means the node on which the loop is running, I node minus 1 into n degree of freedom plus I degree of freedom. Understand that? Which one is the global index and which one is the local index, element index and structural index. I structure degree of freedom is you are picking up the node in structural node. See, because you know LP node I is basically you are picking from the nodal connectivity array, right? Similarly, you can also run a loop over for J node is equal to 1 to number of element node and LP node J. Now, once you identify the index for the column row, we should go to column index. Then you see once again there is a, but the loop over the element is only 1. Please note that, right? So, for J node is equal to 1 to number of element node, LP node J is LP node I element comma J node. Once again for J node 1 to number of degree of freedom. So, J is degree of freedom, J E degree of freedom, and then you have both of the elements. So, element stiffness matrix you are adding with the initialize the structural stiffness matrix, right? So, AS stiff is equal to STF5 plus ES stiff, right? So, each element stiffness matrix you are adding with the initially and initialize the structural stiffness matrix, right? So, end. So, 1, 2, 3, 4, 5 loop. So, 1 element loop, 2 nodal, 2 loop for the node and 2 loop for the degree of freedom over each node. That is the way it is. Now, I have to enforce the boundary condition. So, once again you call the MPX that boundary condition that I have specified a node and the respective the binary variable for each degree of freedom. You see that for I is equal to 1 to M fix, I fix is equal to, if it is 1, then I fix is equal to fix I minus 1. You see that you identify which degree of freedom it is connected to, and respective we have used basically the penalty technique to enforce the boundary condition, because we are multiplying the, we do not want to disturb the structural stiffness matrix. We want to multiply that degree with a large number. That is what essentially we did. In finite element have learned, right, how to enforce the boundary condition without disturbing. One way to enforce a homogeneous boundary condition in this, eliminate rows and column, but another way without but that disturb your stiffness matrix. If you do not want to disturb the stiffness matrix, you just multiply with a large number. That is what essentially we did. You see, you multiply 10 to the power 24, and similarly you have to run over all the 3 degrees of freedom. See, fix I comma 2, fix I comma 3, fix I comma 1 is nothing but a node. That is what you see, that fix I comma 1 is the node over which it is restrained. So, that node minus 1 into n degree, because the node which is restrained, all other degree of freedom between which you have to pass, right. So, that is what fix I minus 1 into n degree of freedom plus 1. Okay. So, you can code it better, but then this is the way I can do. Then I find out the eigenvalue. Why I did find out eigenvalue? Because if you do not enforce the boundary condition, then find out eigenvalue, you will get what? 3 eigenvalue to be 0, because all 3 will give the rigid body mode. So, that is a kind of check in non-finite element code, that is check you must do, right. So, here if you do, then you will see no rigid body modes, no, and rigid body modes will be identified by 0 eigenvalues, right. So, then what I did, I basically find out the global load vector and the load vector, structural load vector. So, once again I run a loop, I is equal to 1 to m, I find out the loading vector. So, II is nothing but loading I minus 1 in, so degree of freedom over which it is connected to, okay. And then I am adding the respective load vector. You see, here I have initialized the load vector, and then you do the static analysis. So, then you solve linear simultaneous equation, displacement you obtain, solving A stiff comma y, nodal displacement, right. Please note that until now we did not talk about the geometric stiffness matrix. We are doing a static analysis. After that, once we obtain the static displacement, we can find out what? We can find out the axial force in the member. How to find out axial force in the member? once again you identify, run a loop over the all element. So in each element x1, y1, x2, y2, length, cos theta, sin theta, and then AE by L, U2 minus U1 plus U1, U1 minus U2 minus U1 plus V2 minus V1, right? You know how to find out axial force in finite element. So here AE by L, C, U2 minus U1 plus sin theta, V2 minus V1. That is the axial force. So we have identified U1, V1, U2, V2 from the displacement. This is the structural displacement. So all the displacement that, so you have to pick up the displacement which is corresponding to that node. So how can you do that? You have the, once again you have the local, we have the connectivity here. You see that you have to identify the node over which it is connected, I1 and I2. These are the two nodes over which the element is connected. So LP node I element comma 1, LP node I element comma 2. Do you see that? Then what we have to do, if you want, this is not important to you. If you want to find out the support reaction, then what you have to do, you have to relax the boundary condition. So the respective term which you multiply with the large number, you have to divide it by that, okay. If you want to, and then you just multiply S tip is with the displacement, you will get the reaction forces. This is important for nonlinear analysis. Here we are not doing that, because when you do the nonlinear analysis, you have to find out the residual forces. So external applied force, the structural reaction. If you substitute then for a perfectly done linear analysis, there will be no unbalanced internal force. External force and internal force must be. These are the very crucial check in finite element. I don't know whether you have, that was been discussed in finite element course. Unless and until you code it, you will never be able to learn finite element. Let me tell you, everything you have to code. Anyway, so forget about that. Now what I will do, I will go once again. Now once you obtain the axial forces in all the member, once again you run loop for the global assembly for the on the geometric stiffness matrix. Similar approach, okay. Here the problem is that I am copying and pasting it, but you can have the subroutine for global assembly, element assembly of stiffness, and call it again and again, okay. But I just, and then once again you have to enforce the boundary condition on geometric stiffness matrix as well, and then you solve the eigenvalue problem, Eigen. So then you see that it's a generalized eigenvalue, okay, it is a eigenvalue problem, in a special eigenvalue problem, A stiff. So total stiffness matrix is structural stiffness matrix, geometric structural stiffness matrix, and then you find out the mode shape and then frequency. You find out the eigenvalues or eigenvectors. Eigenvalues will give you the buckling load, eigenvector will give the buckling mode. You just plot it. Let me run it and show it that it is running indeed. I don't know whether it will run. There is some warning coming, but do not worry about this warning. Let me explain to you what this warning. Warning: matrix is close to singular or badly scaled. Result may be inaccurate. This thing happens because sometimes when you solve this problem, the geometry. What is Arcond? What is Arcond? 1.261 e to the power minus 2. What is Arcond? Anybody Arcond? Matrix is close to singular and you don't know what is Arcond. All of you did numerical analysis, right? Huh? You know a condition number of a matrix? What is condition number of a matrix? Huh? What is condition number of a matrix? Huh? This is very, don't know. You see, these are the eigenvalues, okay. So these values, it is C. Initially I didn't assign the force any, it was only 1, it is coming as negative. You see that minus 7.869 e to the power 16. Of course, it is in Newton, you can reduce, right? So that is the force. First fundamental buckling, fundamental critical load for phi that will trigger buckling. There are the dimension of the stiffness matrix here is 15 by 15. There will be total. So number of eigenvalues will be equal to what? Whatever is the dimension of the stiffness matrix, right? So square stiffness matrix, right? So this is the first mode because this is the lowest, and then it started increasing. And respective eigenvector also you can find out. respective eigenvector you can find out here from there. Well, no, this is the basically you see that diagonal. In diagonal terms, all these eigenvalues are there, right? What is the eigenvector? Okay, VE. Okay, VE. Let me see what is. Yeah, this one. Eigenvector, you can plot it. This is the fundamental one. Okay, this is the fourth eigenvector. You can, because I, 4 I have written, you can find out one eigenvector. You see that some eigenvectors are very small. Why it is so? Minus 70 is minus 18 eigenvector, because these are restraint degrees of freedom. It is almost 0. You see that? Minus 23, minus 20, minus 25, right? Because these are restrained. So there is nothing in that. So you can find out eigenvector, eigenvalue. So this is the structure of the code, and you can all do this thing. Okay, I am removing it. So if you can recall, you can recall that in the finite element assignment, whatever I have shown, using, I have given you this kind of a frame, and this was subjected to some lateral distribution of these forces, and that was also subjected to uniformly distributed forces, uniformly distributed forces. Okay, and I asked you to find out what will be this, what will be the W value for say W value. So once again, this is the frame, and the two-dimensional frame, you can use the same computer code for solving this. You discretize it using element, and try to find out the nodal coordinate, nodal connectivity, element connectivity array, that fixity array and all these things, and then you first solve the statically to find out the axial forces in the member, and then you do this geometric eigenvalue, you construct geometric Stevinus matrix, and then you solve for the eigenvalue problem that is forced to solve for this. Okay, so this problem can be solved. Okay, one point of time, let me recall you, please put your attention and try to concentrate on this, because I can recall once in your experimental method course, once you will see that there is an experiment. I don't know this year whether it is being conducted or not, but buckling of frame. So I can recall that here. So these people were all confused that how to find out the theoretically how to find out the buckling load for a frame, and they were all searching the Timoshenko and this young book and this and that. But then it's very simple using matrix method, right, or finite element method. Okay, so whatever you are learning, try to retain it. Okay, don't it shouldn't be volatile memory, right? In computer there are two, permanent memory and volatile, right? It shouldn't be like volatile memory. You learn and then it evaporates from here. Okay, anyway. Okay, so and that's what I will cover it a little bit, just to sensitize you, the computer programming and things. Now I will just go to dynamic. I will start dynamic stability. Dynamic. So why dynamic stability? What was the problem in the static stability? Till now, when we approach the static stability, static approach of stability, what we have approached to there are two formalism. One is most convenient, and then we loved it, is the energy method, right? Energy method. And then another way, of course, is the equilibrium approach, equilibrium. Directly you solve the equilibrium approach. We have used both the equilibrium approach. Of course, you have to write down the equilibrium equation in deformed configuration or perturbed configuration. So this approach worked well, and then we have solved a number of problems. We have started with toy problem. We have demonstrated the different classes of behavior and different classes of system, and then we have also used the same thing for analyzing the buckling of column, post critical analysis in column, buckling of plate, and post critical analysis of plate, and now everything, right? Both the approach you have followed. Now the problem with the static is that, see, all the cases what we have considered that our loads were all conservative load. Our loading were all conservative. our loading, what is conservative loading? Conservative loading means, there is no dissipation involved on the loading. Okay, when this load is working, on the system, of course the loading, like for a column or for a, for a plate, the load is doing some work, right? The loading is doing because the axial compression or axial compression, it is acting on, out of plane, axial deformation, right? And that is being stored as a energy, strain energy in the plate or in column, right? So as soon as the load is out, that strain energy will also be gradually, recovered. So the energy stored, there is no dissipation of it, there is no work done which will go. You see that? So that is conservative. That means, whatever is the system is path independent, how the load is being applied and things like that, right? And there is no dissipation of energy. An example of the non-conservative force is friction. You see, if you pull a block on a rough surface, that friction force will work on that, right? That force, that work done will never be recovered, right? There will be there is some dissipation. But here all the forces were conservative. Now there are situations in which, the forces may not be conservative, and in that case you will see all this approach, being it energy equilibrium approach, will not work. And that basically took time for the scientists to realize that. So it is not that, in fact all the static method fails, and there was a problem that remained unsolved for a long time, and it was later solved. And the way it was solved is using dynamic. Let me show you that example, how it was failing. The static approach is failing, and we need to know the dynamic approach. And thereby, we have to invite the component which is causing non-conservatism in the system, which is a component of if there is a component of non-conservative forces or there is non-conservative force, then the treatment of stability should include the consideration of the dynamics of the problem. Otherwise, you cannot capture the influence of that. So this fact was not accounted for in the past, and then it was giving false notion and it was giving false result, and people didn't believe, and they was very confused, and then later the problem was solved. So this problem is a column under follower force. Column under which is a follower force. Follower force is a force which follows the deformation. Okay. So for here, what I will take, I will consider a column here. This column, as soon as it is subjected to vertically down, vertically downward force, compression on the column, this is conservative. Even whenever it is deflecting, it was deflecting, if it remain, like this, these are all conservative. This is a conservative force, right? This is conservative force, okay? Conservative force, P vertically downward, P remain vertical, vertical at all instances, At all instances, P remain vertical. However, now we consider the case, however, if P, follows the tangent at the deformed tip, right? At the deformed tip, then what will happen? So if so then you see that there will be a column, this column, and then, and then this, here it is P, that is fine, but as soon as it is coming, then P is following the tangent. You see that P is like this. Then maybe here, when it is coming this, it is following the tangent P, okay? It is coming and it is, you see that the way it is changing, the P is changing its direction. Why? you know, because this P is following the tangent of the deformed tangent to the column at the tip, deformed tip. So this is this is a non-conservative force, non-conservative. This force was not, this case is a case of non-conservative force, okay, non-conservative. This system become non-conservative. Why it is so, that I will explain you, okay. So people will, you know, people started to look into this, okay, this problem. They try to solve using static method, and that they all of them, you know, they failed miserably actually. Yeah, that I will show you, okay, why it is so. So now let us consider and why, how people started solving it and why they were failing. Let me show it to you, and that was basically, then people start dynamic approach. So static approach cannot solve this problem. Fine, you know. So it will have two component. So I am assuming that this angle is phi and this one is delta, this deflection is delta. So P, this will be, you know, P, you know, well, instead of treating this to be phi, I will treat the angle with this, you know, this to be phi, okay. If this is phi and I am still assuming that phi to be small, okay, I am still assuming that phi is still small, so it is P sine phi, it will be nothing but P, you know, P, and this component is P cosine of phi, it can be P. Do you see that? So these are the component forces. So now you tell me one thing. I am assuming that, well, x is defined like this, you know, and my w is here, you know, deflection as a function of x. Now this problem, you know, what is bending moment at any section x? At any section, if I consider any section here or here, what is the bending moment? The bending moment will be contributed by these two components. One, of course, is P first phi, you know, this is P into what will be that? This distance is what? If this is delta and this is small delta, this is small delta minus W, delta W, right? This is, this is going to cause, right? This, so this distance from here to here, this distance is nothing but, delta minus W, because from here to here it is W delta, right? So this is trying to clockwise, right? And this fellow is trying to make it anti-clockwise. So then minus P into phi, and what is at this section, what is this lever, what is this distance? This distance is nothing but from here to here, the length, I am assuming that column has a length of L, you know, I am assuming this column has a length of L, and from here to here x, at a x distance x, this distance is L minus x, right? If I, here it is L minus x, right, M. Then M is nothing but EI d2W dx2, right? M is EI d2W dx2, and another thing what we are assuming, that this column is having, you know, distributed elasticity, but it has a concentrated mass. So the mass is concentrated here. I mean, we do not require to consider mass here, because we are essentially following a static approach. A column under follower force, we are first trying to solve by a static approach. So here what we are doing, we are solving this, trying to solve it by static approach, and see what will happen, okay. So M is equal to this. So here what we can get here, from here is that, so then here you will get, you know, d2W dx2, and then P by EI W is equal to P by EI delta delta, right, minus P by I P L minus X. Okay. So, P by I is equal to lambda square. Let us assume, we have assumed it to be lambda square, right, on the previous example, right. So, I can write this one to be, d2w dx2 plus lambda square delta is equal to lambda square capital delta minus lambda square P L minus X, right. So, that is the governing equation, and then we can have boundary conditions. Of course, you can understand the boundary conditions here. In w is equal to 0, d2w dx2 dw dx is equal to 0. Here boundary conditions at x is equal to 0, here x is equal to 0, w is equal to 0, and dw dx is equal to 0 because it is no slope, and this, and then here the boundary conditions here at x is equal to x is equal to L, w is equal to 0, w capital W, and dw dx, that is the slope, is nothing but phi, right. These are the two boundary conditions, right. Two sets of boundary condition, two sets of at x is equal to L, x is equal to 0, and x is equal to L, right. Now, so the solution of W, of course, is a complementary function plus particular integral. So, complementary function, as you see, d square plus dw. So, you see that d square plus lambda square. So, d plus minus I lambda. So, C1 e to the power I lambda, Euler's equation. So, you can write a cosine lambda x plus b sine lambda x, that is a particular complementary function, and then you can find out the particular integral. So, particular integral, when we want to find out, we will see that how will you find out particular integral. Particular integral will be, or particular solution, 1 by d square plus lambda square delta minus you see that, okay. Here see that 1 plus d square by lambda, I am dividing with lambda, okay, dividing with lambda square, denominator numerator, right, and then I will 1 minus d square by lambda square plus d to the 4 by lambda to the power 4, So, phi minus capital delta minus phi minus this, okay. So, let us assume, so W, this means W is A cosine lambda x plus B sine lambda x, particular integral is delta minus phi L minus x, right. Okay. So, this is the solution that we obtain. Okay. So, let us have the solution, and then we know the boundary conditions over there. So, next class we will try to see. Okay. Thank you very much for today's class.